Hello, everyone. I'm excited to get started with a few ideas about non-parametric data. We have this problem when we have small sample sizes, which in our class shouldn't be too much of a problem. Most of you have your 60 or close to that. But if you do have a small sample size, if you have to break it up into a lot of small groups, if you have data that are just skewed. For example, let's look at the drug data set. I'm going to pull up my graphs and I'm going to create a graph of my scale variable. This Beck depression inventory is going to be my dependent variable. And so I move it over here into the graph. Over here, see how this element properties box pops up. I'm going to check display normal curve. And then I'm going to click on OK. And here we go. Here's my data. So I look at this, okay? This is the drug data set. And I say to myself, this is okay, right? I've got this normal curve, and where the normal curve is high, my data are high also. But then I have a right skew. I have a couple of outliers here who on Sunday scored rather high on the Beck Depression Index inventory. So perhaps that's a problem. What I'd like you to do today is to pull up this drug data set and walk through with me creating this output. You can create exactly the same output that I create and upload that. There's no homework from this data set. I would just like you to understand that sometimes people need to conduct non-parametric tests instead of parametric tests. I started back a little bit in the Beast of Bias chapter, which is chapter 5. In that chapter, Field goes over how to pull up graphs and statistics that might demonstrate that we don't have normality. Remember, we need our data to be pretty normally distributed. We need our data to have pretty equal variances, somewhat close at least, and then we need our data to be independent, meaning that one group didn't influence the other group. They're independent samples. And we show some of these statistically. We test for some of these just to make sure that we're not going too far with our data. Now, if you have a sample size of 100, then even if this graph, okay, let's make another one here. Even if I'm going to reset this, let's do a histogram of my depression on Wednesday. Okay, I want to make sure that I display the normal curve. I really like having that apply. And now I'm going to pull Wednesday over here. Let's look at Wednesday. So we look at the graph and we say to ourselves, it looks like it's bimodal. If I had a bimodal distribution and had 100 or 200 responses, because of the central limit theorem, I could go ahead and say the standard error and the mean of this, because my sample is large enough, are going to be distributed somewhat normally. But here, because my sample is only 20, I have a little bit of a problem. I can look at this and say, okay, I don't think this is going to be normal enough given that my sample isn't large. Another way that I can demonstrate this or look for this is to come here in descriptive statistics, and Field also talks about this in chapter 5. The Explore tab, let me reset this, allows me to just look at my data, and it allows me to look at my data by factor. And this is very important. If you have a data set with 60, but then you've broken age into 10 different groups, and you have gender in 2 groups, and then you're also going to look at year in school, and you've got 4 groups there, you may have small samples in your group that is 60-year-old males who are in their 3rd year of school, right? You can imagine there's only one guy in that group. That's going to give you a problem with normality. Okay, a nice thing about this Explore is I can put both of these in together. Usually, you'll just maybe have one. This is where you'd put your constructs. You may have two or three. You can put them all in together. Before I click on OK, I want to make sure that my statistics are fine. I want to make sure in my plots that I ask for a histogram. And here I want a normality plot with the tests. And here, see this spread versus level with Levine? This is my test for variances. I'm going to do it with my untransformed data. We're not going to transform our data. I know Field talks about this a lot. It is a very great way to come up with some statistical results. But a lot of statisticians and other people warn us that once we transform the data, we've got numbers and ideas that are very, very hard to communicate to our audiences. And so a transformation, while it may show you where you have a significant result, it also provides you with t-statistics and correlations and all sorts of things that don't make sense. Effect sizes don't make sense anymore because you've transformed the data to come up with this. And so you always have to back transform, calculate those statistics in a different way. I mean, you can't recalculate the t-statistic because you'll get a different probability. As you can imagine, it leads to a mess, a lot of extra work, and it leads to your audience members saying, "What? Help!" So we won't transform in this course. It's something to be aware of, but not something that we're going to do. Okay, so when I click on OK, then I get a ton of output. And I'll just pull you through and show you some of the things that I think really matter. You'll find these things in Field's book. The tests of normality right here. So my null hypothesis is there's nothing going on. Like there's nothing that's saying this is not normal. So I really kind of want my null hypothesis to be true. If I find something that's significant and less than 0.05, then what that's telling me is, uh-oh, there's something going on. This is not normally distributed. So sure enough, my Sunday is significant. That means it's not normal. And you saw that. It had these big outliers. What about, oh, and that's Sunday ecstasy. Now, my Sunday alcohol is okay. It's not significant, so I can say it's pretty normal. My Wednesday ecstasy is okay. It's not significant, pretty normal. But once again, my Wednesday alcohol is very significant here. That means it's not normal. And in fact, we'll scoot down here and look at graphs. But before we do, let me just show you. So normality is 1. Having the same pretty basically equal variances is 2. So let's see. Are my Sunday variances equal? Yes, this is greater than 0.05. I might be okay here. What about Wednesday? Yes, this is greater than 0.05. And these different ways of looking at it all agree based on the mean, based on the median, based on the median with adjusted degrees of freedom. All of these things are telling me my variances are okay. So I'm okay with that assumption. Whew. If you remember, independence is an assumption that we don't show with numbers. We show by carefully taking a sample and keeping our independent samples separate, not allowing the same person to be in both samples. Okay, so here's my histogram for ecstasy on, let's see what it's labeled on Sunday. And yeah, that's not too normal, is it? Here's my alcohol on Sunday. That looks a little better. You can see how it's kind of got that peak in the middle. And that's why the test of normality said that one was okay. Then, oh, let's see, come down here and look at we're going to skip down, look at my Wednesday results now. Ecstasy on Wednesday. And interestingly, my test of normality said this is okay. You look at that and you say, that's a mess. But it's good enough. It kind of rises in the middle and flows downward on both ends. Yeah, it's normal enough. but this is the one that came up not normal. It's very much skewed to the right. We have this long tail off the right. It peaks way over here at the left, and then we have these outliers here. So we've done a little of exploring. There's a lot of these plots. Generally, you want these little dots to follow the line pretty closely. Generally, you want this to be kind of a cloud without too much of a pattern. There's way too much information here. Likewise, here's some more information. I really like these box plots because they'll tell you number 13 was an outlier and number 18 was an outlier. I had 2 outliers when it came to alcohol. Always interesting for a potential follow-up, mixed methods, for some kind of a discussion as to why this didn't come out normally, why the variances may not have been equal. Anyway, so that's more information than you could possibly need, but it's kind of fun. Just try creating a few of these and look at them and see what they tell you. So now we are going to, because I decided, okay, there are too many violations of normality here. I'm going to go ahead and do a non-parametric test. I come into Analyze here, and I come all the way down. So scroll, 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 down to non-parametric tests. I have independent samples. Now notice if I wanted to do a paired test, if I have a pre-test, post-test, I could come down here to this next box, related samples. But my samples are independent, and so I'm just going to click here on this independent, and it should open up normally to the objective. And I like to just leave the automatic settings on as they are. I'm going to automatically compare distributions across groups. So I'm not just comparing two means. And part of the reason is because my data are not normal. They're so skewed that the means may not really tell me the story. Now, the computer is going to rank all of my Beck depression scores and actually look at the distribution. Like, did they kind of line up the way that the other one lined up? In other words, did the two groups, so in this case we have the drug and the alcohol, did they line up similarly to each other? Not necessarily normal, but similarly to each other. Okay, here's my field, and I'm going to go ahead and test both of these at once as we have in the past. So I have depression here, depression there, and type of drug, and actually SPSS uploads these pretty automatically. Here are my settings, and I'm just going to automatically choose the test based on the data. Don't you wish everything went this way in SPSS? It's pretty cool. And what SPSS is going to do is going to run this test. They chose for me the Mann-Whitney U test, and that is the right choice. And they actually ran 2 because I entered 2 different dependent variables. So when it comes to the Sunday inventory, they say that I can retain my null hypothesis. Do you see that here? So there's really no difference between alcohol and ecstasy on Sunday. That's what my Mann-Whitney U test tells me, and I can just go ahead. I don't even have to report the significance. I can just say there was no difference on my Sunday test. But look here, on my Wednesday test, I have to reject the null hypothesis. The significance is 0. Now look at this. This is all we got when we ran that non-parametric test. This is not enough information. You know how much we got running other things. So what I can do, and if you have a Mac, you'll have to play with this a little, is double click on this box. I double clicked on test number 2 because that's the one that's significant. And look what comes up over here. I have this nice chart kind of showing me how the rankings looked on this histogram. Okay, so here with ecstasy, I have these 2 numbers that are quite high. I have nothing like that over here in alcohol, and that's one reason, you know, visually you can see they are different. So I look here on this information. It's pretty helpful, although I need to just tell you a little bit that I'd like you to go then. So this information is here on page 226 of the field book. On page 227, Field talks about writing up the Mann-Whitney test. Okay, so here's my total number. Mann-Whitney gives us a U. Okay, so the statistic here is a U. And as Field wrote in his write-up, he says you would report then that U is 35.5. He also reports the Z. I think the Z is optional, but you can report the Z. If you look at this list, where is the Z? And this is one weakness of SPSS. Standardized test statistic is another word for Z. So in this test, you could report Z equals negative 1.11. And that's what he's got there in his write-up. Where are you going to use this Z? Well, look up above on page 227. Do you see that he came up with an effect size? And his effect size right there is 1.11 divided by the square root of n. So he took Z and he divided it by the square root of n to come up with an R effect size. And I tell you, if I had to do this without my field book in front of me, I would forget. So please be gentle with yourself. Of course, after we play with this today, you will forget. I just want you to have practiced it, to have a sense that it's there, it works, it's cool, and if you needed to, you could pull open your field book and you could create a paragraph just like he's got in the writing results section. Okay? I'm trying to think if there's anything else in here that you need. The p-value is here. Okay, the R he calculated. He does report in here a median. And so what you can do is go back. I'm going to close this window here. I always get scared when I close windows in SPSS. But you can go back here into your Explore. Way up toward the top when I was exploring, some of the output included the median. So you could pull the median from there. Call your statistic, the Mann-Whitney statistic, call it a U because that's what Mann-Whitney does. Okay, I hope I'm not making everyone seasick here, but I promise you the median was somewhere in all of this junk. And it's not really junk, but okay, here's the median right in here, okay? So mean, oh, here it is, median. So here's a median of 33.5. Here is a median of 7.5. This is where he pulls the median, okay? A median for ecstasy versus a median for alcohol, because those are the two groups that we're looking at. Much of what this does is it follows the same pattern that we followed with our what we would then call parametric statistics. So a t-test, a ANOVA, regression, those are parametric, and this on the other hand is non-parametric. These poor guys, they got the non in their name. Okay, well let me just show you something else. So this is the Mann-Whitney is like a t-test, okay? Now let's move just really quickly, pull up the soy data set, because the soy data set is something we couldn't run a t-test on because we have all these different groups. I think we have people who had no soy, people who had soy for a day, soy for 4 days, soy for 7 days. Okay, so we've got all these groups. And in fact, our no soy group would be a control group. If we were doing this in ANOVA, we had a normal distribution, we could use Dunnett's. In non-parametrics, we don't have Dunnett's anymore. What do we have and how does this work? Well, turn to field. Now we're going to look at the soy data set starting on page 236. Okay, and this is the last thing that we'll do for non-parametrics. There's a picture of Kruskal, this Kruskal-Wallis test. Okay, in Analyze, we're going to come down again to non-parametric statistics. And we're going to come over again to independent samples. This is exactly where we got our Mann-Whitney test. But lo and behold, this time we're going to end up with a Kruskal-Wallis test. If we go ahead and automatically compare distributions across groups, and if in our fields, here we've got the sperm count, that is our dependent variable, and the number of soy meals per week that each of our participants had, we're going to ignore rank order because this was part of field teaching us how everything is ranked. If you look at ranked order, so here's the third, he ranked them from low to high. So this is number 3. There are only 2 lower than this one. Here's number 4, just a little bit higher. Do you see how he ranked all of those? You don't even need to worry about that because this is what SPSS is doing behind the scenes for us. Okay, so we've got the right variables in there, and then here in settings, right now, we're just going to let SPSS automatically choose the test based on the data. We click run, and we're just going to get that same little box that we got before, right? So here's our little box. We got this little box right here, and we're going to reject the null. Well, come on. First of all, they don't even tell us that the Kruskal-Wallis test now is an H. An H. I don't know who. Maybe that's Mr. No, his name is William. Maybe that's his middle initial. Maybe that's his wife's initial. Anyway, you don't have to memorize these things. But I want to know more about this test. I need to know more because if you turn to page 249, where Field tells us how to write it up, he's got more information. Okay, so first of all, you can do the explore test, right? And when you explore this data, you'll get a median. You'll have information on whether the data were normal, on whether the data had equal variances. So remember, that's the Levines, that's the Kolmogorov, Smirnov. But I went ahead and double clicked on this box over here so that I could have more information. Well, this is kind of cool. This is showing me my 4 different groups and how they're different. Okay, so these are my 7 meals per week, and visually they look different, don't they? Here's my no soy meals, my 1, my 4, and my 7. I had 80 in this analysis, but because I had 20 in each group, then once again it's kind of a small sample size, and that's why Field went ahead and used non-parametrics here. My test statistic here is an 8.66, and if you look at Field's right up here, he has an H, so on page 249, a capital H with 3 degrees of freedom. See the degrees of freedom right here in parentheses equals 8.66, and then he's got P equals 0.034. Okay, so that chart to me is a lot more straightforward than the one that comes with the Mann-Whitney U or the Wilcoxon, which we didn't talk about the Wilcoxon, but that's another option. There are hundreds of options. Okay, but this is not enough information for me because if I was in ANOVA, then I would either do a Tukey a post hoc test, maybe a Dunitz post hoc test. I would do something to follow up. Well, now follow me down to the very, very bottom of this page. Here I have my Kruskal-Wallis test, and here I have fields, and here I have view. Under view, I can actually, right now it's got the independent samples test view. I'm going to click on pairwise comparisons, okay? Here is my view right here, and ta-da! Here are my post hoc tests, okay? And Field goes ahead and he reports these. He talks about, come over here for significance, okay? Where are the significant results? Well, 7 meals versus 1 meal. That's less than 0.05. 7 meals versus 4 meals. That's less than 0.05. 7 versus none. That's less than 0.05. So when you start looking at 7 meals and you compare that to none, to 4, or to 1, you have significant differences. And so that's what then he goes ahead and reports these. He reports the p-values, he reports R effect sizes, and he goes ahead with this adjusted significance to report them. You really, once you start running these non-parametric tests, you have lots of decisions to make, lots of ways you can report these things, and you can read through Field's arguments for why he reports them a certain way, why he uses the effect size he uses, and then make some decisions on your own. I mean, certainly this is something you may never do, but if your committee asks you to, this is something I would recommend. Not only taking Field's word for it, but looking at what others have done, especially in your area, in the journals that you would like to publish, and even online through some of the different great informational videos out there, like Khan's Academy. Okay, well, I just wanted to give you a taste. I think this is way more than a taste. This may have been a meal of this fascinating area of non-parametric statistics and how they work in SPSS. To me, this is not intuitive. The fact that you would come down to the very bottom of the page and ask for a different layout. Here we go, different view. Okay, but there it is. That's where you'll find it. Have fun with this. I look forward to seeing your output when you're done.